Hey guys, these are USB-C power banks and I really like to use these power banks for powering my electronic projects. However, they do come with a problem because if I implement electronics that is really power saving or that go into sleep mode or standby, then these power banks tend to turn themselves off after some time. And there's a workaround for that. The workaround basically is that you draw some current in regular intervals for a certain duration of time, and that basically keeps the battery pack alive. Usually you determine these parameters manually. However, I thought it would make a really cool project to actually make a system that determines these three parameters automatically. So a system that determines the interval time, the current that needs to be drawn, and the duration the current needs to be drawn to keep one of those battery packs alive. In this video I will explain you the build. I hope you will enjoy, and let's get to it. I start by drawing up some architecture. I hope this will help me keep some overview. I have my USB-C power bank here. I am planning on connecting it to a USB-C trigger board using a relay, so the microcontroller can turn the pack back on when the pack has turned itself off. When the power bank is off, the system will still need power, which I am planning on supplying using the supercap. Since USB-C can supply multiple voltages, I first want to boost the USB-C voltage to 24 volts and then buck it back to 16 volts to charge the supercap with. The microcontroller is of course the brains of the system, and it measures both the voltage on the USB-C line and on the supercap. If the supercap has been charged, the microcontroller can detach the system from the power bank by using this MOSFET, and it can then accurately control the load on the power bank using this constant current load. User I/O I'm planning on implementing using a debounce button and an LCD screen. The microcontroller also controls a discharge circuit to be able to drain the cap after use. Time to design the circuit in KiCad. I will have PCBs made for this project because I don't want to spend my days soldering. I put the LCD screen in and make sure I can turn it on and off using the microcontroller. I need charge pumps for supply to the op amps that control the current load. Of course, the boost converter. I connect some signals to the microcontroller, and this is the voltage controlled constant current load. I make a resistor bank and use a Darlington transistor array to charge the supercap. The cap drain circuit. I use a thyristor to make sure it drains completely. Et voila, we have a PCB design that more or less implements our architecture. When they come in, I unpack them. They look good. Assembly begins. It is great to be able to fast forward this, as it takes quite some time in reality. I also do some measurements, of course, when configuring the DC to DC converters. When everything is finished, I write some code to do some testing. First a constant current load, then charging the cap. Then cutting the boost to see if we can unload the pack so that it turns itself off. It does. However, we also found that one relay is unfortunately not sufficient to turn the USB-C pack back on. And so we initially implemented a very annoying way of drawing user attention to manually turn the pack back on. However, later we just use an array of relays to switch every line we need separately. And this does turn the pack back on. In the end, we have a working system that is far from perfect, but is a good start for further development. Here's a complete cycle of parameter determination on a power bank by this system. Of course, first it needs to charge the cap. This takes some time, so I fast forward. And in the end, when the cap is sufficiently charged, it stops charging. I then press the button and it starts determining parameters. It starts with determining the main cycle time. It does this by simply unloading the power bank and waiting for it to turn itself off. The system then turns the battery pack back on by switching the relays. It then continues with determining the minimum current draw duration, in which it uses the bisection method. That means, given some upper and lower bound value for current draw time, It takes the middle point and just tries this amount of time. If the bank turns itself off, the system knows this middle value is the new lower bound. If the bank stays on, the system knows this middle value is the new upper bound. This way it homes in onto the actual minimum current draw time needed to keep the bank on. In this case we find 187 milliseconds. It then continues with finding the minimum current to draw. Here it uses the same bisection method, but now each time trying the mid value for current. And so it homes in. In this case we find a minimum current of 34 milliamps. In the end it displays the parameters found. So that's it for this video. I hope you all enjoyed it and maybe you found it inspiring somehow. And I hope to see you back in the next one. Goodbye guys.